Hi, thanks for coming to my poster. My name is Jonathan Keefe, and I'll be presenting a project that I did with my advisors, Viola, Stoermer, and Brady, as well as a collaborator at UCSD, Jonas, and a collaborator at National Research University in Moscow, Igor Utochkin. The title of this project is Information about All Items is Actively Held in Mind when Computing Ensemble Statistics about a Set. So, ensemble perception is the ability to extract summary statistics about a set of stimuli, such as the mean orientation of objects or the variance in their colors. This process of extracting summary statistics is typically characterized as being effortless and independent of individual item information. However, it's not entirely clear that this is the case. So, in the present work, we asked how much information is held in mind when computing summary statistics about a display in order to get to the bottom of this question. Because this information is not available by analyzing behavior alone, we measured how much information subjects were holding in mind by recording EEG while they performed an ensemble perception task. In particular, we measured the contralateral delay activity, or CDA, which is the lateralized negativity over posterior scalp that indexes how much information is being actively held in mind. That is, as we can see in the figure from prior research, plotting the CDA difference wave, the CDA increases in magnitude as more information is held in mind. Using the CDA, we measured how much information subjects held in mind while performing a typical ensemble task, which was adapted to match visual information across the two hemifields of the display. On each trial, subjects were given a cue indicating which information they should remember in the following presentation. This cue was immediately followed by a bilateral presentation of oriented triangles. In this trial, subjects ignored the triangles on the left and remembered the triangles on the right. Then, they maintained this information over a 900 millisecond delay and reported a probed orientation. Subjects did 3 tasks in this format in separate, short blocks. A task where they remembered just one triangle and reported its orientation after the delay. A task where they remembered 4 triangles and reported the orientation of a randomly chosen triangle on the probed side after the delay. And a task where they were simply asked to compute the mean orientation of 4 triangles and report that mean, after the delay. Subjects always knew exactly what task they were performing, and we made sure to emphasize the differences between the remember for and report mean tasks to ensure that they didn't simply adopt a single strategy to perform both tasks. Now, before we look at the CDA, let's look at the behavioral results to make sure that subjects could do each of these tasks. Here, I plotted the error of reports in each task, with error on the x-axis and number of reports on the y-axis. As we can see in each of these plots, subjects were very good at each task. It's worth noting, however, that the x-axis of the remember for plot is plotted such that errors toward the mean of the set are positive, and errors away from the mean of the set are negative. In this plot, we can see that subjects were not simply reporting the mean of the set in the remember for task, as we can tell from the difference between the actual reports in the solid bars and the simulation of what the reports would look like if subjects were only reporting the mean, plotted in the dotted line. However, subjects were biased toward the mean of the set. And for more information about this biasing effect of the ensemble, you should see poster 476 by Igor Utochkin and Brady. Now, let's talk about our CDA predictions. If ensemble processing is effortless and independent of individual item representations, then we would expect subjects to hold only one item in memory over the delay, just the mean. This means the CDA should be the same in the remember one and report mean conditions. However, if ensemble processing is effortful and dependent upon maintaining item information, then we would expect subjects to hold all 4 items in memory, the whole set. This means that the CDA should be the same in the remember for and report mean conditions. So now let's look at the CDA to see how much information subjects were holding in mind. What I've plotted here is a difference wave of the ERP. The y-axis is microvolts of neural activity. The x-axis is time from array onset. And there are 3 lines plotted, one for each task. The gray area is our a priori time interval for the CDA. What we see during this time interval is that the CDA is the same magnitude in the remember for and report mean tasks, with that magnitude being much larger than in the remember one task. This means that subjects were holding the same amounts of information in mind when asked to report the mean and remember for objects. So, to circle back to our predictions, this means that ensemble processing is effortful and that we extract summary statistics by holding information about all items of a set in mind. This is really surprising, given that prominent models of ensemble perception typically assume that information is processed rapidly and quickly dropped when we compute summary statistics, not maintained at all. We have to ask, why might this be? Well, it could be that the tests used to probe the presence of individual item representations have been insensitive to whether this information is actually present. Often, these memory tests seem impossible, even when all of the information is concurrently present, and the task is simply one of perceptual discrimination. However, we think that these findings can be explained with the population coding account of ensemble perception, where information about all items is present in the population of neurons coding this information, but location information is essentially dropped. We can use this population level information, even without the locations, to extract ensemble statistics. This account is particularly helpful in that it can explain how we're able to extract the mean, variance, and even range of a set of stimuli without implicating several different neural mechanisms for rapidly extracting this information. We can extract this information because we're still maintaining it. And that's it. Thank you very much for visiting my poster. Feel free to reach out with questions or comments via email or Twitter. And if you'd like to see more about what we're doing in the lab or see what's going on with this project in the future even, feel free to check out my website or the lab website. Thanks a bunch.